professor at the University of Western Australia, and I've got a few pictures here to share with you that I guess show you what I do when I'm out in the field. To be honest with you all, I spend, I don't know, maybe less than 10% of my time actually doing this fun stuff, and a lot of time sitting in front of my computer looking at the data. So, you know, the stuff that is, well, for me, incredibly fun, the practical side of actually being in the field, it is actually a small percentage of the time that I spend doing this. I also teach, so I teach into several programs at the University of Western Australia. So I teach into environmental engineering, where I teach them fluid mechanics. I also teach into the marine science program, and also we have a new two new masters, or relatively new masters master's programs, one Masters of Ocean Leadership and another one the Masters of Oceanography, which I teach into both of those as well. So, you know, in an academic lifestyle, we're kind of dividing up our time always between the components of teaching, which is obviously incredibly important because we want to educate people to go out into workforce, into various roles, to help, or in my case, feel very passionate about the ocean and its protection and longevity. And we also spend about half of our time on research. So I also have 6 or 7 PhD students who are studying different aspects of oceanography, and I mentor and supervise their projects. So a lot of my research is in the deeper ocean, but not the very deep ocean. So you would know that we have what are called continental shelves, and on those continental shelves we have our coastal seas. And so I pretty much do my research in water depths from 0 out to about 500 metres or so. And around Australia, these continental shelf regions are incredibly important to the ocean's productivity, so the production of fisheries and so on. They're also key to many of our tourism industry and, you know, protection of things like coral reef environments and so on. But what I'm focused on is understanding the ocean dynamics. I'm a physical oceanographer, which means I'm trying to understand the physics of the ocean, so how ocean currents change, how they interact, and also the very small scales, so ocean turbulence. So we're thinking down to sub-millimetre scales. And, you know, I'm very biased in my opinion, but I think that the ocean physics is incredibly important because obviously it plays a big role in the entire understanding of the globe. And we're going to talk a little bit about this today. But it also plays a role at a very fine scale in terms of the movement of nutrients to our ecological systems, and also things like the movement of larvae. So it actually plays a very critical role in all of our marine biology and our ecosystems in the ocean as well. It's very different from a terrestrial system where, yes, we do have the wind moving things around, but the ocean is a much more connected place. So if I advance this ahead, there we go. Today I'm going to talk to you about ocean heat and how this is changing. And I'm going to also tell you a bit about how we observe these changes, and then finally talk about a specific location of the ocean, which is the shelf off Northern Australia. And in that context, I'll talk to you about the occurrence of marine heat waves. So we'll start with that overview of ocean heat content and talk about why it matters. So if we look at the global ocean, and this is a picture showing you the sea surface temperature, just a snapshot at one point in time. we can see this distribution of heat at the surface of the ocean with very warm temperatures extending out from the equator, and then very cool temperatures closer to both of our poles. And this, of course, is no surprise to you. You're all very familiar with this, but the important aspect of this is that these gradients in temperature from the equator to the poles leads to the setup of the global ocean circulation. So that gradient that we just saw in the sea surface temperature between the warm temperatures at the surface at the equator and the cool temperatures of the poles leads to this global ocean circulation. So that water that cools at the poles then sinks down to the bottom of the ocean, thousands and thousands of meters. And you see then it takes these pathways that go back towards the tropics before it comes back to the surface in the warm regions around the equator. And I'll just make sure you can see what I'm indicating. And so, you know, we see that again in the Atlantic Ocean, where you have this cool water that's produced in the Northern Atlantic that sinks down to the bottom of the ocean. So this blue water is at the abyssal depths of the ocean, and then rises up in regions of the ocean where we have mixing occurring that can then bring that warm water to the surface. So this is the component of the ocean that stops the ocean just from becoming one stagnant pool, all of the same temperature and salinity. But the thing is that because we're, you know, raising the temperatures of the atmosphere, and the ocean has the capacity to absorb a lot of this heat, we're changing the way that the ocean is operating. So the ocean has done, you know, a great service to us on Earth in that it's absorbed 90% of the warming that's occurred in recent decades, and that top part of the ocean is storing as much heat as the Earth's entire atmosphere. So we're going to think a little bit about this concept of storage of heat now. Oh, sorry. First, I'm going to tell you about the consequences of this increase in ocean heat. So one of the key things that will happen and is happening is sea level rise that's occurring through the thermal expansion. So as the water is warming, the sea level is rising as a consequence. We also have then an indirect effect, which is the also leads to sea level rise, and that's resulting from ice melting in the poles, in the polar regions. We're also seeing changes in the activity of our major storm events, such as cyclones, because they take heat from the ocean to generate and grow their energy. And so we see increases in intensity in these types of storms with a warmer heat content of the ocean. And then, of course, we know about the ecological influences of warmer surface temperatures on average, and also increases that we're having in the occurrence of marine heat waves, which lead to those intensive periods of much higher temperatures. So what exactly is heat content? Well, you would know that the ocean has layers of different temperature. So just like, you know, if you had a swimming pool and you didn't have the pumps turned on, then during the day with the sun coming down onto the water surface, the very surface of the water is going to heat, and that water underneath, if you dive down to the bottom of the pool, is going to be much cooler. So this is the same thing that happens in the ocean, but over thousands of meters then, where we have this warm surface layer and cooler water underneath, and we call this the ocean stratification. So what we can do then is we can measure the heat content by taking the sum of all these different temperature layers over the different depths, and making a calculation called an integral, which is basically the sum of those temperatures over the depth, and we multiply it by the density of the water times the specific heat. And these two things are more or less constant in the ocean. And so it's this temperature and depth component that is changing with location and changing in time. So the ocean heat content gives us a measure of how much energy from changing temperatures of the ocean is actually stored there, whereas something like the temperature is just telling us what's happening in terms of a change at a particular depth. So if we look at our satellite images of the sea surface temperature, then we just know what the temperature is at the surface of the ocean. So this ocean heat content is then a very powerful tool for analysing change. And so if we look at these figures here, we can see that over time, and here we're going from 1990 up to 2020, we can see that the shallow in this definition being between 0 and 700 metres depth, the ocean heat content has continuously increased over this period of time and increased quite dramatically. You can see here that there's a lot more variability in these different analysis of the ocean heat content. So this is coming from a range of different locations, so different analysis, I should say, so from different organisations. And this is because our observations of the oceans were not so good. And so it was more difficult to know that our calculations were good, even, really not that long ago. So this change in ocean heat content is also occurring in our deep ocean. So you can see in the depths greater than 700 metres, we're also seeing this steady increase in the ocean heat content. And that is in response to what's happening at the poles, where that water is interacting with the atmosphere, but then sinking down to abyssal depths and then spreading out across the ocean basins. And so we can see in these deep regions of the ocean, we also have influenced the ocean heat content over time. So we can look at this in a spatial context as well. So this is looking at the ocean heat content in 2020 relative to a long-term average, which we'll think of as the kind of climatology or the base rate. The baseline. So we can see areas that are red here. We've had an increase in the ocean heat content. And there are some blue areas as well where there's actually been a decrease in the ocean heat content. So this region, for example, around the equator in the Pacific Ocean, we can see there's actually been a decrease in the ocean heat content. All right, so how do we actually measure the changes in that ocean heat content? So in order to fully quantify the global heat, we need to measure temperature everywhere at all depths and at all time. But of course, this is not actually feasible. So instead, we have to use limited amounts of data to paint a picture that gives us the best certainty in this analysis. So what we do is we take very sparse measurements and we use techniques that allow us to effectively interpolate between where we have measurements and then produce a grid of the ocean temperature at all depths and across the global ocean. And the way that we get these sparse measurements is we have observations that are ship-based. So we have instruments that we put over the side of ships that take profiles of that measure the temperature as well as the pressure or the depth. And Obviously, the technology that we have to do this has changed immensely from times, you know, where data was taken of temperature by putting a bucket over the side and collecting the water in that bucket, and then back on the deck using a thermometer that usually wasn't calibrated particularly well to measure the temperature, to more sophisticated current technologies. So this is showing an XBT, which is a method of firing off a instrument that is done in an expendable sense, and it sends back the data to the ship, and the instrument is considered expendable. We also have a large array of floats, and these floats actually can control their buoyancy to descend the depths of the ocean and back up to the surface. And they use satellite communications then, you can see the aerial here, to send the information back via satellite to various locations where the data is collected. So this allows, I mean, this photo has a ship here, but this allows these floats to actually operate completely autonomously, and they stay in the ocean for as long as they survive, collecting this data and sending it back without any intervention from humans. And we also have locations that are very difficult for these robots to get to, and these are particularly areas under ice shelves. And so we utilise different animals, such as these seals, to actually be able to take these observations. So you can see on this seal's head here, a little device which can measure the temperature and pressure, and has a little aerial on it that sends, again, the data back via satellite. And so these give us really useful observations under locations such as under ice shelves. So this is a little bit more information on the Argo float program. So all these black dots are showing you the floats that were in the water. This is on the 1st of September last year. So you can see we have almost 4,000 floats at this time across the global ocean, and you can see that there are some regions where we don't have as many observations, but the floats now are at a reasonably large density, such that we can create this gridded data with actually quite a bit of confidence. You know, this is not without a large amount of investment, and this is certainly a global program that Australia participates in. We also can use moorings, and many countries, including Australia, have a system of or a network of moorings, and these moorings have a bottom weight to hold them in place. So you can see these big train wheels, which are used as the bottom weights, and they are deployed in the ocean over extended periods of time to collect data. They can be set up to be doing it in real time and sending the data back, but this is expensive and requires a surface buoy to be at the mooring, and so that comes with its risks. And so sometimes, or quite often around Australia, our moorings are recovered every 6 months, and then we get the data back at that point. So we're going to have a little, oh, this is actually showing you, oh, sorry, I forgot this is a movie. This is showing you a little movie of how we put a mooring into the water. So this is one of the moorings that my group has put out last year. So it's maybe slightly different instrumentation, but you can see we start with the top of the mooring and the floats that will be holding it taut in the water column. And then we go through to putting the instruments in line. And finally, we end with putting that bottom weight in, and then it all kind of sinks down to the bottom. So the bottom weight is sitting at the seabed, and then it's held taut by the buoys above that. So this is the type of data that we collect from these moorings. So this is showing you a mooring that is in water depth of 200 meters, and this is on a shelf, in a shelf environment. And the red dots are showing you data that is collected over 1 day. And there's lots of processes that cause quite large changes in temperature in locations such as this data was taken on the Australian Northwest Shelf. And so we have processes like internal waves, which cause really large fluctuations in the ocean temperature. But on average, this black profile is capturing what is happening to the change over that time. So we're not really interested in the higher frequency processes. We're actually interested in something like the ocean heat content, being able to quantify the long-term changes, so the low frequency processes. Okay, so now we're going to have a little look at what we can do with mooring data in a location like Northwest Australia to understand events such as marine heat waves. So typically when the typical analysis of marine heat waves has relied on the sea surface temperature. And the reason for this is that we have satellites that measure the sea surface temperature, and they take measurements in some cases at a frequency of up to every 10 minutes of the entire sea surface at resolutions of a few kilometres. So you can see this is a very valuable resource and a very valuable product. But the problem is it's only giving you what's happening at the sea surface. So what we wanted to do with this little study was to see how often is the sea surface temperature actually a reflection of the ocean heat content, so that integral or summed parameter, and yeah, is the sea surface temperature representative enough, or do we need to have something that's more detailed if we want to understand what's happening below the surface? And of course, when you think about it, the subsurface is incredibly important because that's where everything's living, right? Nothing really lives right at the surface of the ocean. We actually all of our organisms are living below it. So if the sea surface temperature is high, but actually below that it's not too bad, then our organisms might be okay. And vice versa, you could potentially have a scenario where the sea surface temperature was not that warm, but the ocean heat content, so that summed effect of the energy from the temperature was large, then you can have organisms that could be under a lot of stress at that time. So the questions we wanted to answer with this little study was, how do we characterize or identify subsurface heat waves? And is the subsurface heat wave then correlated with what we see at the sea, with the sea surface temperature? And we're going to focus on this period of 2020 to 2022. And this is really the period where we've had the La Nina continuing, and we've seen continuously warm temperatures, certainly atmospheric heat waves occurring on the west coast, but we also see warm ocean temperatures in northern Australia. And we're going to particularly look at this marine heat wave event that occurred in January 2021. So what we do with marine heat waves is we use a very kind of statistical definition to actually say that it's a marine heat wave. And so you have to kind of exceed thresholds and sustain that for over 5 days for it actually to be classified as a heat wave. And this is very similar to the way that we classify atmospheric heat waves, so heat waves that are affecting our lives and the way that we live. What we need then, of course, is some comparison level, and this is what this blue line here is. This is showing you what we call the climatological value. So this baseline is taken from the average of very long-term records. So we take records over a decade and say this is the climatology. And then when we have exceedances, we're looking for exceedances that have a duration greater than 5 days. If they're less than that, then they're called a heat spike. Now, this is all defined on sea surface temperature satellite as the product that you're using. So in this study, what we've used is a combination of mooring data from our national mooring network, which is run by the Integrated Marine Observing System. We've used climatological data from both the Atlas of Regional Seas and also the sea surface temperature climatology is coming from the Atlas of Australasian Regional Seas. And the sea surface temperature satellite product is this Himawari product, which is available every 10 minutes in our region. So you can see an example here of the sea surface temperature anomaly. So anomaly being the difference from the background, from the baseline or that climatology. And you can see here in January 2021, so the average over that month, that we have anomalously high temperatures over the much of the northwest shelf region, and particularly the largest anomalies occurring on the southern northwest shelf, close to Ningaloo and extending offshore towards Barrow Island and so on. And these are the locations of the moorings that we'll use data from. Okay, so as I said, explained before, we can calculate the ocean heat content from our mooring information. And then we can produce these time series where we're comparing that ocean heat content. So the mooring ocean heat content is this red line here. And the blue line is showing you the climatology. So that's showing you the baseline ocean heat content. And down below, you can see what's happening with the temperature throughout the entire water column. Left a scale off here, which is very bad practice, but our yellow colours here are showing our largest temperatures, and our kind of purpley colours down the bottom are our cooler temperatures. So you can see how that's changing, how this stratification is changing over time, over this quite long time series that we have here. And in the top figure, you can see the data from the satellite. So I think, so what I want to indicate to you here is that we have these periods of time where we have quite an anomalous ocean heat content. So you can see the red line is above the blue line. And this is indicating over this quite extended period of time that we have a lot more ocean heat in this region, and this is this northern mooring here in the Browse Basin. And if we look very closely at this, at our sea surface temperature, we can see that this is that January 2021 marine heat wave event, and you can see there's the sea surface temperature spiking, and it's also at a time when the ocean heat content was high. But what's interesting is after this peak passes, we have sea surface temperatures which are now normal, so they're following the blue line, but the ocean heat content is remaining much higher than the climatological value. And so we can see that this is sustained over much longer periods of time. And this is similar. If we go south at the Raleigh Shoal site, we see a similar thing where we have high sea surface temperature events confined to the January region, but the ocean heat content is remaining high over a much extended period. And finally, further south at this Barrow Island mooring, we see the same thing where we have sea surface temperature exceeded, but followed by a much more extended period where the ocean heat content was larger than normal. So if we take these three sites together and compare them to what we see from the satellite sea surface temperature data, we can see that in January, which are all of our blue lines here, we had definite peaks in our sea surface temperature, but during April, the temperatures were much cooler at the surface. So we can see that we have, in fact, negative anomalies in most of the cases and only a weak anomaly in the south. but these corresponded to periods where we still had a subsurface marine heat wave. So this is indicating that there's a problem with our sea surface temperature being used to indicate the occurrence of marine heat waves. And if we look over a much longer record, which contains the marine heat wave we experienced in 2016, we can see that also during this period of time, we had an ocean heat cont that was far exceeding the climatological average. And this is for this mooring that's up in the Timor Sea, further to the north. So if we take all of the data that we have and we compare the sea surface temperature, so that's from our satellite data, to the moored information of the ocean heat content, we can see that there's not a strong relationship between the sea surface temperature, which is what we currently use to identify marine heat waves, and the ocean heat content. So we can see it's really not a good indicator of what's happening below the surface. The good news is, though, that when we take the sea level anomaly, which is data that comes from another type of satellite, this is a satellite that actually measures the deviation of the water surface of the ocean. And this is a height then in meters. So you can see it's quite small. It's only up to 25 centimeters exceeding the mean and down to 5 centimeters below it. You can see there's a very strong relationship between this sea level anomaly and the ocean heat content. So this means we can use information that's collected by satellites, which is, well, of course, satellites are expensive, but they're running, they're operational, they're there to actually make a much better prediction of what's happening in terms of marine heat waves below the surface. So what are our subsurface marine heat waves and when they're occurring? And I've just indicated the temperature in the colour here. So you can see that over this range, it can be any temperature virtually at any of these ocean heat contents. So in summary, the ocean heat is affecting most physical and biological processes. So it is a really important thing for us to understand. There's a very clear response of the ocean heat content to rising levels in carbon dioxide in the atmosphere. And we've also demonstrated that the ocean heat content can be very useful for us understanding subsurface marine heat waves. To continue to have good measurements of the ocean heat, we need a lot of very expensive observations. So we're talking about robots that profile those Argo floats. We're talking about moored instrumentation, IMOS being the Australian example of these. We're talking about satellites, which obviously are expensive and usually owned by multiple nations. And once we have all these observations, we can do a much better job of managing our changing ocean. And I wanted to leave you with this because I know that a lot of this information is you know, not painting a very positive picture for you. But as an oceanographer, what I'm working on with my colleagues is trying to develop methodologies that allow us to understand what is likely to happen in the future. This helps us, of course, to, you know, make a stronger message about what we need to do to reduce our overall effects on CO2 in the atmosphere, or contributions of CO2 in the atmosphere, which is important, I think, from a you know, in a global perspective. But we're also working to come up with products that allow management to occur in a better way. So we're doing things like, you know, with this marine heat waves, we're trying to utilise the understanding that we have to come up with seasonal predictions of what the ocean temperature might be. So this would allow a fisheries person then to say, well, we need to close a fishery for this summer. We need to move these aquaculture pens into a different region. It also allows, some of the information we're collecting also allows us to make better use of the way that we select locations of our marine parks in our oceans. So, for example, if we know an area is likely to be more protected because of the physical oceanography, so some areas are because of the ocean processes, there's a lot more cooling and they lead to regions that are kept on average cooler, then we should protect those regions because there then could be the regions where organisms can spread out again into regions of the oceans that were hit by a marine heat wave, for example. So, alongside this kind of message of, that's quite negative in understanding what's changing with ocean heat in our ocean, I hope you also can see that with this knowledge, it empowers us then to be able to make better decisions going forward. So that's the end of my talking, and I would love to take any questions.
Thanks, Nicole. Yeah, we had a presentation a few weeks back from Nick Caputi of Department of Fisheries, basically, who was talking about the impacts on fisheries and the need to have that. Yeah, like basically going forward, we need to be able to predict. So it was really tied really well in together, these two presentations. One question, the syllabus that we're looking at states the link between ocean warming and stratification. Have we seen any observable trends in like an increase in stratification?
Yeah, that's a good question. So it depends where you are in the ocean, but that is definitely something that oceanographers are looking to define. So there's two things that we're really concerned with there. One is changes in the depth of what we call the ocean mix layer. So close to the ocean surface, there's a layer that receives a lot of energy from the atmosphere. And because of this energy, there's a lot of turbulence in the water column, and this causes lots of mixing. And so even though you've got the sun, pushing its solar radiation into the ocean, there's all these other energies from the wind and from the cooling that occurs at nighttime, which is a convective process. So just like, when you boil the kettle, you see all these big bubbles being formed in there. So these mixing processes lead to a layer at the surface of the ocean that's quite well mixed. And so one of the things that is being studied very carefully is this depth of the mixed layer changing? So that's part of the characterization of the stratification of the ocean. And then underneath that surface mixed layer is a region which has a very large gradient, okay? And we call that the pycnocline, or the thermocline if we're just referring to temperature changes. And that layer, so the intensity of that layer is incredibly important as well, because the stronger that stratification is at that thermocline or the pycnocline, the harder it is to mix things across it. So you can see that is another essential component of the stratification. So these are the two things that are being studied very carefully. Now, one of the problems with that, as we've kind of highlighted a little bit, is that we don't have long-term records that are reliable of these changes. So really, it's only since we got our Argo float program that we could start to measure these changes. And then there's a lot of variability within the ocean that is in that signal as well. So natural variability, oscillations like our El Nino, Southern Oscillation and so on, that are in their record. If you don't have anything longer, we've got kind of 20 years of Argo data, it's hard to really discern what is natural variability versus what is long-term change at this point. But yes, a lot of effort is going into that.
So yeah, because it seems to be more like we continuously hear this marine heat waves popping up in the discussion, especially with the blob of Northern America and and also the East Australian heat waves as well. So much linked to the El Nino Southern Oscillation Index, and well, I guess what I'm hearing you say is that we're now we might now have the equipment and data to collect, to understand it more, but now we just need the time frame to be able to predict, what are the causal factors.
Yeah, I think yes, I think you're right. I think it can be quite difficult to unpick exactly what is the cause. But I guess what is very clear from that ocean heat content data is that the energy stored in the ocean from increases in temperature, so that ocean heat content has increased remarkably. And so this means that on average, everything in our ocean is becoming warmer, but these more infrequent events, the marine heat waves, the research is showing, the data is showing that they're becoming more prevalent, so they're occurring more rapidly.
Okay.
And so, yeah.
And is that caused by like an intensification of an El Nino or a La Nina event, or is it we're not sure why, we know that we're seeing more heat waves?
It depends on the heat wave. So the northern Western Australia, so the waters that we were looking at, they tend to be the marine heat waves tend to correspond with strong La Ninas. When we get our marine heat waves from Exmouth south on the west coast, they tend to correspond with El Nino cycle. So that it's very variable depending on the location, depending on the connection. There's also obviously a very strong impact of the local heating as well. So and this is the thing about the ocean, which is another kind of key takeaway for you all, is the ocean is just so connected in a global sense. And so what happens, some very long distance away can have a large influence on what's happening at your site. And so understanding those connections is incredibly important, and something that we need more good minds to be focused on.